Battery manufacturing plant, lithium-ion. Lithium-ion battery cells are widely used in various applications such as electric vehicles, portable electronics, and renewable energy storage. The manufacturing process involves several steps to ensure the production of high-quality battery cells. The process consists of electrodes preparations, cells assemblies, and quality control stages. Electrode preparation. The first step in the manufacturing process is the preparation of electrodes. Electrodes are typically made of a combination of active materials, binders, and conductive additives. The active materials such as lithium cobalt oxide for the cathode and graphite for the anode are mixed with binders and conductive additives to form a viscous slurry. Electrode coating. The slurry is then coated into a current collector typically made of copper for the cathode and aluminum for the anode. Coating techniques include doctor blade coating, slot die coating, and roll-to-roll coating. The coating process ensures a uniform and controlled thickness of the electrode materials. Electrode drying and calendaring. After coating, the electrodes go through the drying process to remove the solvent and binders. The drying process can be done through the various methods such as convection ovens or infrared heating. Once dried, the electrodes undergo calendaring, which involves compressing the electrodes to improve its density and adhesion. Separator preparation. Separators are essential components that prevent direct contact between the anodes and anodes, ensuring safety and preventing short circuit. The separator is cut and shaped into specific sizes and formats suitable for battery cells assembly. Cells assembly. Cell assembly involves the stacking of multiple layers of electrodes and separators. The layers are assembled in a specific sequence, with the cathode, separator, and anode repeating. The assembled layers are then compressed and rolled into cylindrical or prismatic shapes, depending on the battery design. Electrolyte peering refers to the process of adding an electrolyte solution to a battery or electrochemical cell. This process is crucial for the operation of various types of batteries, including lead-acid, lithium-ion, and others. The electrolytes facilitates the movement of ion between the anode and cathodes, enabling the flow of electric current. Common in lead-acid batteries, sulfuric acid solution, and some lithium-ion batteries. Solid electrolytes used in solid-state batteries for enhanced safety and efficiency. For peeling process, the electrolyte is carefully added to the lead acid to ensure the proper coverage of the electrodes without spilling or overpeeling. The peeling process must be conducted in controlled environments to avoid contamination and ensure safety. Correct peeling ensures optimal ion conductivity, directly affecting battery efficiency and capacity. For safety, overfilled batteries can lead to pressure buildup and leakage, while underfilled batteries can result in dry out and potential cell damage. Once the cell is assembled, it undergoes electrolyte peeling. The electrolyte, typically a mixture of lithium salt and organic solvent, fills the space between the electrodes and separators. The peeling process is done in a controlled environment to ensure proper peeling and avoid contamination. Cell sealing. After electrolyte peeling, the cell is sealed to prevent leakage and maintain a hermetic environment. Sealing techniques includes the heat sealing, ultrasonic welding, or laser welding. Refers to the process of securely closing and protecting battery cells after they have been assembled and filled with electrolyte. This is the critical step in battery manufacturing, ensuring safety, performance, and longevity. Here's detailed overview. Here is the key aspect of cell sealing. Purpose of cell sealing: prevent leakage. Sealing prevent the escape of electrolyte, which can lead to performance degradation and safety hazards. Protect from contaminants. A sealed cell is protective from moisture, dust, and other contaminants that could affect performance. Maintain internal pressure. Proper sealing helps maintain the necessary pressure within the cell, especially for certain battery types like ion battery. For sealing method, welding, commonly used for lithium-ion batteries, where the cell components are welded together using ultrasonic or laser welding techniques. Some cells are sealed using specialized adhesive that provide a strong bond and help prevent leaks. Involves using heat to melt and fuse layers of materials together, commonly used in punch hell. Mechanical sealing uses screw, clamps, and other mechanical means to hold the cell components together securely. For the quality control, leak testing after sealing cells are often subjected to tests to ensure there are no leaks. This may involve pressure tests or immersion in water. Visual inspection, checking for any visible defects or irregularities in the cells. Ultrasonic weldings uses high-frequency vibration to create localized heat bonding materials without additional adhesive. Ideal for thin materials, ensuring strong seals without damaging the battery components. For laser welding, provides precision and control, allowing the hermetic seals of battery cells, which is crucial for high-performance applications. For adhesive sealing, epoxy and silicone adhesive are commonly used, chosen based on their chemical resistance and thermal stability. It can be applied using automated and dispensing system to ensure consistent application and reduce waste. For heat sealing, involves heating an edge of the bound materials until they melt and fuse together. This method is efficient for creating lightweight and flexible battery packs. For mechanical sealing, provides a strong physical connection, often used in cylindrical and prismatic. For material consideration, barrier materials must be chemically resistant to electrolyte and provide a barrier moisture and gases. Common materials include polythene, polypropylene, and aluminum laminates. After sealing, the battery cells undergo an initial formation process. The formation involves subjecting the cells to specific charging and discharging cycles to stabilize their performance. Once formed, and cells go through the rigorous testing, including capacity testing, cycling tests, and safety tests. Formation and testing are critical stage in the battery manufacturing process, particularly for rechargeable batteries. These steps are ensure that the cells meet performance specification and safety standards before they be deployed in application. Formation process. The formation process involves the initial charge and discharge charging of a battery cells to establish its performance characteristic. Key steps in formations. Initial charging. The battery is charged for the first time, which initiates chemical reaction within the cell. This step is crucial for the development of the solid electrolyte interface. The battery undergoes several change and discharge cycles. This helps in balancing the capacity between cells and ensuring uniform performance. For voltage monitoring, during formation, voltage levels are closely monitored. This helps identify any cells may be underperforming or have defects. For temperature control, the formation process is often conducted in temperature-controlled environment to ensure the optimal chemical reaction and prevent overheating. In this process, the purpose of formation, stabilization, establish stable electrochemical properties within the cell, enhancing performance and lifespan. Capacity matching helps in matching capacities among cells in a battery pack, ensuring that all cells perform optimally together. For testing procedures, after formation, extensive testing is conducted to verify the performance and safety of the battery cells. These are the common testing types. Capacity testing. Measure the total energy capacity of the cell, ensuring it meets design specification. This is typically done through a series of charge and discharge cycles. Internal resistance testing. evaluates the internal resistance of the battery, which can affect performance and efficiency. High internal resistance may indicate defects or degradation. For cycle life testing, assess how many change and discharge cycle the battery can undergo before its capacity falls. For temperature and humidity testing, evaluates performance under various environmental conditions to ensure reliability in real-world application. For safety testing, include tests for short-circuit condition, thermal runaway, and puncture tests to ensure the battery can withstand extreme conditions without failing. For batch testing, random sampling of cells from production batches to ensure quality across the entire production run. Automated testing system, use of advanced equipment to perform tests quickly and accurately, providing consistent results. Important of formation and testing. Performance assurance ensure that the battery will perform as expected in their intended application. Identifies potential safety issues before the batteries are assembled into pack or used in a device. Help manufacturers meet industry standard and regulation, enhancing product reliability. Quality control checks are conducted throughout the manufacturing process to ensure the cells meet the required specification and standard. Once the cell pass quality control, they are packed into the modules or packed depending on the application. The final packaging includes insulation materials, protective casing, and electrical connectors. Quality control and final packaging are critical steps in the battery manufacturing process, ensuring that the product meets safety and performance standards before reaching the market. For quality control involves systematic process to ensure that the battery cells are packed meet specific standards throughout the manufacturing process. Incoming material inspection. All raw materials, electrolytes, electrodes, separators, etc. are inspected for quality and compliance with specification before product begins. In process quality checks, continuous monitoring during production including visual inspection and dimension checks. So what is visual inspection? Visual inspection, checking for defects in electrodes, separator, and cell casing. And the dimension check, ensuring components meet size and thickness specification. For formation testing, as previously mentioned, there involves initial charging and cycling to establish performance metric and identify any defective cells. End of the line testing. Final testing conduct on completed battery pack includes performance testing, verifying capacity, internal resistance, and cycle life. And for safety testing, conducting short circuit, overcharge, and thermal runaway test to ensure safety standard are met. Final packaging is crucial for protecting the battery cells during transportation and storage as well as providing necessary information to customer. Key aspect of final packaging, protective packaging. Batteries are packed using materials that prevent damage from physical impacts, moisture, and temperature variation. Common materials include foam insert to cushions, individual cells, or pack. Plastic wrapping to protect against moisture and dust. For labeling, each package must be clearly labeled with battery specification such as voltage and capacity, safety warnings and handling instruction, QR codes or barcodes for tracking and inventory management. Packaging must adhere to international shipping regulation for hazardous materials, especially for lithium-ion batteries. Proper labeling to indicate that the package contains lithium batteries along the handling instruction. For importance of quality control packaging, safety assurance prevent defects that could lead to safety issues such as thermal runaway or leakage. For performance reliability, ensure that the battery performs as expected in real-world application, enhancing customer satisfaction. So, that's all the 9 stages of lithium-ion battery cell manufacturing process presentation. First is the electrode preparation, electrode coating, electrode drying and calendaring, separator preparation, cell assembly, electrolyte filling, cell sealing, formation and testing, quality control, and final packaging. Thank you.